Westinghouse Electric Corporation. Dr. Carelli received his PhD from the University of Pisa in 1966 in nuclear engineering. He's been with Westinghouse for over 30 years. He is responsible at Westinghouse for all their advanced reactor technology development, and he is the originator of the IRIS concept, which is a Generation 4 reactor for the very near future. And that's the topic of his presentation today. And please welcome Dr. Carelli.
Thanks, Adi, for the introduction, and thank you for inviting me here. I really, the mic is on this side.
That's okay.
It's okay? Yeah, I'm really glad to be here and talk about IRIS, and I'm kind of excited because this is the second time I'm going to present IRIS to not a family. Till now it's been in the family. The first time I was at the ICONE 8 conference in Baltimore in April, and at that time really what we presented was the proposal that we won the contract. And in this, since then until now, we completely changed the design. So now you are my guinea pigs. I'm testing the new design that we have, and you're going to hear about. You've already seen first one. Let me give you. First of all, I'm sure by now. On this side. By now, you know what the Generation 4 reactor is. I'm sure, but. The Generation 1 are the early experimental reactors, the gas graphite. Generation 2 are the current operating reactors, basically the BWRs. Generation 3 are the wishful thinking of the next generation, passive reactors, the AP600, EPR, advanced boiling water reactor. And the P1000, the Westinghouse now working, is another group parallel to mine, is working on the P1000. And then Bill Marwood, the fourth, came with the Generation 4, reactors, which are the ones that really are beyond these generations. And essentially, the Generation 4 are supposed to address 4 objectives. And again, it's only coincidence is that Bill is building the fourth Generation 4 and 4 objectives, just a coincidence. And the Generation 4 essentially is proliferation resistance, enhance safety, improve economics, and reduce waste. And of course, this always been there. What has been new has been the proliferation resistance. This for the first time, really, you had to make a design addressing the issue of proliferation resistance. And at that time, the question was, what the heck is proliferation resistance? It's a nice word, nice motherhood, but how do I design it for a motherhood? How do I quantify? And you see what we have done. And the history is that a Navy program solicitation came in end of 98. And I know that because I spent my Christmas vacation working on the proposal. And it's becoming now a trend. The proposals are all coming, and you work on Christmas on writing proposals. So, and at that time, we established a STAR consortium formed by Livermore, Argonne, Los Alamos, Westinghouse, and MIT, California, Berkeley, and Texas A&M. And what we said, let's look at various types of these Generation 4 reactors. And we picked it up, we split. Livermore worked on molten salt. Argonne worked on lead bismuth, liquid metal. We worked on water, and Los Alamos worked on gas. And then what we said, we are going to work out these reactors for 18 months. That was our proposal. And then we do a down selection, and then we pick up 1 or 2, and for the next 18 months, we work with only down select. That's what we proposed, and the DOE down selected for us, because the only one that was approved was the LW. And there was the one, and the STAR LW means secure, transportable, autonomous reactor, light water. Okay, actually, originally they said, let's call it star W. And I said, well, W, no, it's water and Westinghouse. So it became a little more Westinghouse, the LW. And one thing that, I felt pretty good was that at the end, about the 45 proposals so won, there were 3 generation 4s to be selected. In the Westinghouse, all 3 of them. Okay, so I really felt good. We celebrated. Because 2 of them, we were prime. We were the one who were responsible for those. One was this star LW. The other one was on the liquid metal reactor coupled lamp tech. Very sexy idea. I'll tell you another time. And the third one is the encapsulated nuclear heat source, which is cooled, like bismuth cooled, and California Berkeley is the prime, and we do the engineering. But anyhow, that's the history. Now, after we won, I changed, and I didn't like star LW, so I changed the name, and I called Iris. And basically, the reason I called Iris, besides it's prettier, okay, it's a good name, but I want an I as the first letter. And I, they say it stands for Italian. No, it stands for international. Okay, it stands for international because I truly believe that the days that somebody like Westinghouse design a reactor and sells is over. Okay, it cannot do in a country, it has to be globally. That's the only way. If you just pull out the resources, that's the only way that really you can have an economic and viable product. So from the very beginning, I said that we're not going to do just as U.S. has to be on international page. And then it came the name. And after we chose Professor Lombardi from the Politecnico Milan, who is a part of the team, was one of the founders of the team, we discussed the name, and he was smiling, and he said, yeah, it sounds good. And when we finally decided, yeah, that's a good name, he said, my mother's name is Iris. Okay, so that cleans you. And I'll give a little bit more on that. But to tell you what, just so you can follow the discussion, to put in perspective, Iris is a modular 100 to 300 megawatt electric. An integral design is a pool. It's not a loop type. It's a pool type, water cooled. Okay. And what we did, and that was the approach we had from the very beginning, is forget what has been done, because we want to have a new reactor that addresses those 4 objectives. But if we keep thinking the old way, essentially you do some improvements, but don't do a quantum type. And water nuclear, to have really a relaunching of nuclear, we have to have a quantum leap. We can just go by incremental improvements. So the idea was, has to be light water, and that's I think one reason why of the 4, only ours was selected. The light water, what it does, it gives us a technology base. We don't have to reinvent the technology to demonstrate the technology. We have a zillion reactor years of operation between LWR, PWR, and BWR. So we can use the technology. What we have to do is to re-engineering for the year 2000, the next generation, or that blah, 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 or that good motherhood. But the idea basically is think different. Okay, that's the real, and you'll see as I go through, how we've done, and we're still in the process. We're still in the process of this, but that's really is the focus. So once we did that, we decided what we want to do. Okay, we selected a name. Okay, and then it's the question of priorities. Okay, the next thing was to have a logo. And so we had the logo, and that is, we have all the flags, international, the Iris, and all the participants are going through that. And then going in order of priority, the next thing was to have a PR. Okay, so we have a cat. And this was done by the Italians. We have a cat with Iris, with the flags. So at this point, the only thing we're missing is the design. Okay, but the most important things we had already. And here's the team. And the team really is something. I apologize, probably from over there you can't read it. But basically, we started with the original team, that was the proposal. It was us, California Berkeley Professor Greenspan, MIT Professor Todrias, and Professor Lombardi from Milan as a member. That was the original team. And you have who is doing what and so forth. While we were writing the proposal, JPC, Japan Atomic Power Company, which is the Japanese utility for advanced reactors, we were already writing the proposal and say, well, we'd like to participate. And when they came, I had already written about 80% of the proposal. I say, well, hang on a second, let me finish the proposal. If we win, then we'll talk. And in fact, they joined us in September. Essentially, the grant was given end of August. So right away, JPC said, we're going to participate. When the abstracts of those 46, 47, whatever winning proposal was published by DOE, about a day later, my phone started ringing of people that wanted to participate. And so MHI joined pretty soon, and then there was the CA Kadarash that joined. Okay, BNSF didn't have a choice. They bought us. Okay, so they didn't have a choice. They had to be in. So eventually they got in too. And then was the Tokyo Institute of Technology that joined, and then Bechtel, because one thing we're missing was an architect engineer, and Bechtel joined, and recently, a couple of months ago, University of Pisa, Italy. What is important here is the only people that are paid by DOE are Westinghouse, UC Berkeley, and MIT. Everybody else are doing on their own money, okay? Which is a kind of testimony that if somebody, you go to your feet and you go to your pocket. So these people are putting in people and money to work on IRIS with us. So it's because they believe on the concept. So let us say he made it. At least he told us we're on the right track. This is a scheduler. And when the first time I put in, they started questioning my mental sanity. Okay, because they said, how can you have this in 10 years? And my answer was, either you have in 10 years or you can forget about it. Okay, and the reason is this. If you are looking at nuclear power, demand versus supply, all the stuff. But basically is the demand that say goes some, little bit fuzzy up, so depending what countries. BNFL has done this. BNFL say, okay, this is a good idea, but let's see really what it is. So there is one guy at BNFL spent about 6 months now working on this. You look at different market areas, 8, he divided the world in 8 regions and so forth. And there was a general consensus that in the year 2010, there is a kind of a drop in the power generated by nuclear. Okay? Because basically you have a lot of reactors that are getting out of commission, are shut down by the Greens, all the stuff, and even accounting for the license renewal, there is a big mismatch between the demand and the supply. So you want to have something by that time, and whoever gets there in 2010 and demonstrate it works, you have, the right of first refusal. You are there. You've got the market, and that's the important thing. So if you're coming 20 years later, okay, the market is already been taken. So that's what I'm saying. What I want to do is to have, in 10 years, to have an IRIS deployed. Okay, and I believe we can do that for just the reason I said at the beginning. We're not going to have a technology development. We're going to have engineering development. In engineering development, if you put together a bunch of people with a good brain, you have it. If you have to demonstrate and run an experiment, and the experiment doesn't run and so forth, you don't control the time. If it is engineering, up to a certain level, you can control the time. So, 2002 is the end of the NERI contract. That's at that point, the NERI granted to Westinghouse and university is over. At that point, there is something. Either we say, hey, they will say, nice, we had a lot of fun, that's it, another paper reactor. And I worked with so many paper reactors in my life that I don't want to have one more, okay? So at this point, what you have to do, something has to happen. And what has to happen is, yes, this technically and commercially, it makes sense. At that point, you really put a lot of effort on, you do an actual design, and in 3 years, I believe that we can have an actual design ready for construction. For construction, we can construct 3 years, tops 2 to 3 years. You see, Iris is modular, prefabricated all the stuff, and we go from there. Okay? So, by 2010, I want to have a first of a kind. I don't call it a prototype, because a prototype is something you're demonstrating the technology. Again, over and over, I'm not demonstrating technology. I have a first of a kind of an Iris line, and we're going through on what little bit that is. So, what I wanted to go is how have you addressed those 4 requirements: proliferation resistance, enhanced safety, improve economics, and waste. Okay, that's really how that has been driving the design. The proliferation resistance was the primal drive of the design. And that's what the thing they say. When we started, it has to be proliferation resistant. And I said, what does it mean? And the answer was shrugging of the shoulders. It has to be proliferation resistant. Okay. So we are the one who, in the consortium, the STAR consortium, started putting numbers. We had to design for numbers. And what I said, okay, proliferation resistance means you keep the fuel has to be up to 20% of reach precise. Okay, if it is below that, it's okay. If it's above, it's not good. So you have to keep the fuel out of the host country. Say it's a third world country and you don't want to have the fuel going around. So if you have a core that you don't manipulate, you don't shuffle, you don't refuel, you just plug in and take out and put a new one, under control of the designer, of the Iris consortium. That is proliferation resistant. Okay, that's one attribute. And at that time, in the proposal, I said, well, we did some preliminary evaluations and said we can leave a fuel for 15 years. And after we start doing actual work, 15 years was a bit stretch. So we compromised with 8 years. What happened was with 15 years you can do it, but it's not terribly economical. And the main thing is if you don't have an economic plant, it's the best proliferation resistant plant because nobody's ever going to build it. Okay? So I want to avoid that. And you agreed. They say, yeah, as long as you go with that concept of not refueling, not shuffling, just in and out, that's okay. 8 years is fine. The next was inaccessible reactor, because fine, you have the fuel there for 8 years without shuffling, but you go and open up the reactor and play around and pass around every year. You still have access to the fuel. What about if we design a reactor that you don't have to go there that often? Okay? And then these are intrinsic safeguards. Then there are internal safeguards, whatever it's called. Then there are the external safeguards. External safeguards basically are IA inspectors, guards with machine guns, and attack dogs, okay, basically. And of course, what we can work in is on the safeguards in terms of the IEA. If the fuel is delivered and taken back by the consortium, so you have a control on that. You have to leave the fuel in a pond to be spent, to decay and so forth. Only one core load at a time. After 8 years is cold enough, we can take it back. Another thing is, right now, what you put in the pond, in the cooling pond, are a bunch of assemblies in individual rows. If we have chunks of assemblies, then the IA inspector has to keep track of, let's say, 15 and 20 instead of a few hundred assemblies. So anybody can count up to 20. Okay, it's more difficult to count up to 700. So that again helps the kind of the external safeguards. But the most important thing here is that proliferation resistance is not a technical attribute, it's political. And honestly, I hated to design it for political stuff, because it changes, and I design it for political stuff, and say, hey, now, we have a new administration, new Congress, we change our mind, and I'm stuck, okay? So what we've done from the very beginning is the proliferation resistance as an asset rather than necessary evil. Instead of having designed it, say, oh shucks, now we have to do proliferation resistance. We do that from the beginning. And what has to do has to be economical and has to improve essentially the operation of the plant. So 8 years, what it gives me is a shutdown every 8 years instead of every 18 months. That means less O&M. Okay? In an accessible reactor means I have to have online maintenance and diagnostic. And right now my target is every 4 years we do maintenance. So basically what we have a plant that runs for 4 years and it's a shutdown every 4 years for maintenance, every 8 years for maintenance and diagnostic. That cuts down on O&M. If we can do that economically, it makes sense. So at this point, the proliferation resistance is icing on the cake. They say, we don't have proliferation resistance anymore. Okay, what I have is an economical plant with a good O&M. Okay, that's really the approach. The other thing we have, our design, we're burning MOX. And again, if people start, flying all over, I say, oh, you can't do that in that box. There is now MOX and plutonium stocks all around. And basically you get the MOX, they kick you on the behind. They say, please take the MOX, take the MOX. So at this point, I have a plant here is designed to get rid of the MOX, which is good because we eliminate the plutonium, but also is good economically, because it's something that's laying around. Okay? And in terms of waste, we have about 50% of the waste of the present plants. So we have also waste reduction. So the proliferation, as I said, is an asset. Now, how do we do a long core life? And the way we started in the proposal was with this line here. Okay, and the tighter the lattice, first of all, we go with a triangular pitch. Triangular pitch is a lot more compact than a square pitch. The tighter the lattice, the less water you have, the less moderation, and so the easier is to have a flatter reactivity curve. The big thing is to have a reactivity let down as flat as possible, so I can let it go without having a 50% delta K to live with at the beginning. And that's what we had in the proposal. And actually it's true. And in fact you have, this is the curve for a tight lattice, the one above is for regular PWR. Okay? After a few months, when we started doing the neutronics, we found out that with the tight lattice was fine in terms of the reactivity letdown, but it just happened at the end of life, the Boyd coefficient was positive. We should have thought it, but hey, it didn't, it came out pretty up. There are ways of accommodating. But then we say, okay, what about, let's look at what happens on P over D. And here is the discharge burn-up. Basically 8 years is this arrow here. 70,000 burn-up is roughly 8 years. That's our target. You can do that with a very close P over D, or you can go over-moderated. Actually, this here is the current PWR, which are on the bottom of the curve. That's in the worst position of this. If you go up this way, you can have the burn-up at the 8-year lifetime with a very well-moderated reactor, neutron spectrum, and then the Boyd coefficient is negative. Okay? The other thing too, what happened also, we started the design with something like 18-19% fissile, because it was within the limits of the 20%. Then when we had the first annual review with DOE, I was sitting next to Madeline Feltus, and And the guy that was doing this was presenting this measuring, just nudged me and said, "You really need 18%. I said, "Measuring is within the limits. Now you have 20%. I said, "Well, can you do something better? Less than 18%. Okay? And then when I start thinking of that, if you look here, this is 10%. Okay? Actually, with 10%, the over-moderated is much better, even in terms of the discharge burn-up than the tight lattice. So the tight lattice makes sense for a high-level, fissile level, while the over-moderated is better on the lower level. And then the clincher was, if we go to something like a 2 P over D, you can use the MOX fissile that is fabricated at Sellafield by our company, by VNFL. Okay? So we had everything was clicking. And so, and this, now it's simple, but it took us quite a bit of time. So we have zeroed in on a core design. Has a long life, is well moderated, has a negative reactivity coefficient throughout life, and a P over D around 2, we can use the MOX Sellafield, which makes our owners pretty happy. Now, this is technology for the first iris. It's based on existing technology, well moderated, light water, MOX is fabricated, everything is fine. In subsequent irises, and that is one concept I want to, right now the reactors, you have a PWR, let's say 20 years ago, you had a reactor, and you kept selling, Westinghouse, the GH, kept selling the same stuff. Iris is modular, okay, it's a small module. I can have an Iris 1 based on current technology. The next time in Iris 2, I'm improving something. So if something keeps evolving, and we can keep improving and have a better product as we move along. It's easy to do with this type. And in fact, here we already have found that if you take with the tight lattice, if you take a sandwiches of fissile and fertile, like plutonium and U-238 tails, and you play around with different sizes, different thickness of these sandwiches, you can have a negative void coefficient, even with tight lattice. Has to be worked out. It's not current technology. It's something to be for Iris 2 or 3, or whatever. What is important is that in the same core, later on, I can go in and put in an advanced tight lattice. Now, out of the same module, I either have more power or have a longer lifetime. Okay, so it's something they say that we can keep on working, and then we have this better product. And that is one of the things that the role of universities is critical, because California will be working on these sandwiches. So even after we have our design, they keep on working for the next generation. And now safety. That's the next one. This is one that is extremely important, because again, this is the one where really we start, as I said in the beginning, we start looking at things from a completely different angle. And here is our philosophy. Generation 2, current LWRs. You have an accident, and the reaction is, well, we have an accident, let's see what we can do actively to take care, to cope with the consequences. You spray, you flood, whatever. With Generation 3, IP600, AP1000, so you say, okay, I have an accident, I'm going to cope with the consequences. Instead of pushing a button or opening up a valve, I have passive systems. Okay? My idea is with Generation 4, you don't cope, you eliminate the accident. Okay? And that sounds like a tall order. You say, well, you're dreaming up. But actually, it can be done. If you really look, and if you look at it from a different angle, it can be done. And there is one thing I wanted to, maybe I'm kind of specifying here. But when we're talking of safety, there are two aspects. One is the quantitative. You go to NRC and you say, okay, I have this, and you defend the safety, you have got all this, it is a probability and all of that. Fine. There is another aspect. That's the PR, that's the public acceptance, That is what the public does. Okay. You go to NRC and you say, before we have a core-disruptive accident probability of 10 to minus 6, whatever. And now the super-duper design now is 10 to minus 8. Great. You go to the public and you say, now it's 10 to minus 8. That's a reaction. So what? 10 to minus 6, 10 to minus 8, 10 to minus 4, the public doesn't make one bit of difference. If you tell to the public and say, hey, this can't happen, it's just not a question of probability. It doesn't happen. It's a completely different reaction. Okay? So, with that in mind, what has been our approach is we have a new design. Let's look at this design and let's take advantage of having now a new design and see what we can do with this new baby in our hands. Okay? And let's try to eliminate the accidents. Of course, you're not going to have 100%. Nobody's perfect, not even me. Okay? So there are still some left. And the one that left, now you have a passive means. And we spend quite a bit of time on this. But I think this is the thing that I'm the most happy. That here is the actions. The most action we have. Now, Iris, and what I have here is the Iris design characteristic, the safety implication, what is the accent, what we do. And what we did is say, let's look at what Iris looks like. What we have? We have an integral configuration, a pool type. The steam generators are inside the vessel. The pressurizer is inside the vessel. There are no piping, no large piping going out. So the large loca is gone. You can have it. You break a pipe inside the vessel, you break a pipe inside the vessel. That's it. So the large locas are gone. Okay? Score 1-0. Okay? The next one is, because I put the steam generator inside the vessel, steam generators are pretty tall. I'm going to end up with a tall vessel. Okay? So now, how can I use this tall vessel to my advantage? One thing is obvious. If you have a tall vessel, the thermal center distance increases and you have natural circulation. That's obvious. Doesn't take a lot of IQ to get there. So essentially you're taking care of loss of flow accidents. You know, a pump seizure, loss of electrical supply, that type of stuff. Either you have two things. You can eliminate the LOFA altogether. If you have full natural circulation, you don't need pumps. Okay? Or you can make acceptable what we call a partial natural circulation. So you have enough natural circulation to go over the hump of the accident, of the transit. So stay below the limit, and you have like 10, 20, 30%, whatever it takes on natural circulation without having full natural circulation. We look at both, I will show you the result. The other thing is, if you look at the drawing, you have the core, you have the steam generators, and you have a good 10 meters of a control rod drive lines, which is a waste of space. Okay? Now, what about if I put the control rod drive lines mechanism inside the vessel? Instead of going through the head like a porcupine, the vessel looks like a porcupine, all the control rod drive lines are going out. Okay? I have them inside the vessel. What happens is that the control rod ejection, which is a class 4 accident, okay, is gone, is eliminated, because you have nothing to shoot out. One additional thing is, if you look what happened on PWRs, they have the corrosion on the head. How many reactors have gone down to replace the control rod, seal, and drive lines on the vessel head? All that headache is gone. Okay? So, these are eliminated. Then, okay, let's keep looking at what Iris looks like. The vessel has to have now the steam generator inside. So if you compare with the PWR, okay, the vessel is, for the same power, is larger, because now you're sticking the steam generator inside the vessel. That means that I have a lot of water inside the vessel. So with this lot of water, this large water inventory, if I run to the transit, I have basically an accumulator there that takes care. It slows down the transit, by definition. Okay? and you have more water to keep the core covered. But then there is another thing, that the vessel is now larger, but the containment, you have nothing else to put it there. Because if you look now at a PWR, you have the vessel, you have the steam generators, you have the pressurizer, you have the containment. The steam generators are gone, the pressurizer is gone, there's a bunch of other stuff that you can compress. So the containment is much smaller. So now what you have a larger vessel in a smaller containment. Okay? A smaller containment, much reduced size of the containment, I can have a high pressure containment. And I'm going to show in a second what that means. Okay? That's again just looking at what we have, what we have in our hands. The final thing is the refueling accidents. You drop an assembly and so forth and put it in place, and they are reduced because you do every 8 years, you refuel the core instead of having partial refueling. The important thing here on the locus, here we're talking not large locus, because they are gone by definition. We're talking the small locus that experience has proven over and over, they're minor, and they're the ones that always are killing you. Look at Riemann Island. Okay? So the small locus, we have a core uncovered, remaining covered throughout with no safety injection. Okay, and that I think is quite an accomplishment. Okay, and at this point I have to be okay. One second. Let me do this. This is the layout of the iris. So that's what I was saying here. If you look at this, you're talking a good 10 meters here of just the drive lines. Okay, that's what I was saying. There is a lot of wasted space. And essentially you have the core. And this one shows is with the control rods inside. Now, I was talking about natural circulation. When I wrote the proposal, I thought that I really needed a lot of natural circulation. So we said, okay, let's have boiling, because of course increase the delta rho, so you have a lot of driving. And let's lower the inlet temperature and increase the delta T. If you increase the delta T, you have less flow rate, which means less pressure drop. Okay, so the combination with boiling and low inlet temperature, I'm going to have quite a good natural circulation, which is true. What happened, however, was we found out that you could have a natural circulation, a full natural circulation, if you had a vessel that was probably about 50 or 60 meters high. Okay, so it's not terribly appealing. And also the boiling, we had something like 15% or so quality of the boiling, which means average, a lot of boiling. So we say, really, because if you look at the literature, a lot of people have really done studies and work on full natural circulation integral reactor. And when we started really running the numbers, it doesn't really make sense, economically and operational wise, to run with full natural circulation. Doesn't make sense. Let's have instead a partial natural circulation, to go over the hump of the transits. And let's say we pick it up 20%. It has to be demonstrated. We have to do relap analysis, all that. We haven't done that yet. There is also another reason that I don't want a full natural circulation, no pumps. Because at that point, if you don't have any pumps, okay, essentially the cooling of the reactor is at the mercy of natural circulation. Let's suppose you start having some deposit or something, and you have a bypass of the natural circulation. Instead of going all the way up nice to the steam generator and back, let's say you have bypass, you set up a natural circulation through the core. You're gone. Okay, if you have a pump, I always push a button and I have a pump. So if you think that safety-wise, you have both active and passive, which I think the safety makes a lot of sense, to have speed pumps with the natural circulation. Now, on the containment. This is what it looks like. You have EP600 and you have nice containment. We pick it up as sphere, and this is just a thin shell equation. What that means is by being a sphere instead of cylinder, I can double the pressure. And since I have half of the diameter, or half of the radius, I can double the pressure again, 4 times. That means that the containment in iris can take a pressure at least 4 times higher than the containment of PWR. And right now, the containment of the PWR is 3 bars. So in iris, we can take 12 bars. Actually, since it's smaller, you increase a little bit the thickness. Since it's a small sphere, it doesn't cost that much. So you can go to 15 bars. Okay? So now you're talking about a containment that you can spike up to 15. At this point, what we're going to have, we can really cut down the load. At this point, I have to apologize if I'm not going in the details, because this, I think, is a cornerstone of iris, and we are going to have a patent and so forth. And since this is going to be taped and sold on the streets, so I'm not going to tell you how we did it. Okay, so that's sorry. It will be sometimes we have it, but essentially, out of this consideration, okay, we came up with a design. Essentially, that's this. This analysis were run by the Polytechnic of Milan with their proprietary code, and I'm going to give you the name of the code here. Okay, so but anyhow, a 4-inch break loca is the worst that you can have. And we took a break above the core, which is the worst position. And here is the spike in the dry well, in the containment. And we went to something like 120 psi, which is what, 8 bars, something like that. So we really had room to spare, because we could spike up to 15. But here is the result. Here's the beauty. What we have here is the differential pressure between the reactor vessels and the containment. After something like 15 minutes, essentially that pressure, the differential pressure is 0. You don't drive out the loca anymore. And actually in this area, we change from a loca to a coca, gain of coolant axis. Because what happens is, we are putting water back in the reactor, back in the vessel. Because the pressure in the containment is higher than the pressure in the vessel. And you're pushing the steam back inside the containment, it condenses, it goes in the core. Okay? So, essentially, and then if you look, this essentially goes on and on. Okay? And we ran only to 40,000 seconds, which is about 11 hours. We found out that our leak out of this 4-inch break is 4 gallons an hour, which, if you do some quick calculation, it takes about a month, 34 days to uncover the core, if you don't do anything. Okay? And here is the level. Here's the level of water. Here's the core, and here is the level of the water in the core. So essentially, it stays about 1 meter or more above the core. The core is all covered all the time. No safety injection. It's nothing. Okay? This is iris doing all things by itself, because of the design we've done of the containment, what we've done there. So you have the core covered all the time for a very, very long time. So this is basically the thing that, hey, you really have something here in terms of safety, because what it does in terms of economic is forget about all the sprays, forget about all the safety grade systems. And safety grade systems are the one that cost money. It's simple. You don't have to do all the Ruby Goldberg type of stuff. Forget about. You don't have a safety grade, and the thing works takes care by itself. And it's based on first principle. It's not something that say you do this and this works. This is based on first principle. I only tell you this. This came just looking at the perfect gas law. We look at the perfect gas law and say, how can we use it? The iris geometry with the perfect gas law. That's it. That's how we came with our design. So in terms of improved economics, which is the important thing? Actually, it's not the important thing. It's the only important thing. Because it doesn't matter how safe it is, how proliferation resistant. If it doesn't cut economically, forget about it. It's another paper reactor. Beautiful, it looks good. I can take with me to the grave That's about it. Okay? So, what do we want to do? You want to be at 3 cents a kilowatt hour. That basically is a kind of the bar that you have to go underneath or be there. How do you do that? Well, capital cost. The integral reactor vessel means that I don't have a separate pressurizer because the pressurizer is inside, and so all the cost is gone. All the piping and valves that you have in the loop is gone. Inside is much reduced, so you have that. And the safety great. Safety is beautiful, you have a safety, and also it's economic. That's the thing, you always have to have synergies in things. You don't want to have a safety and cost you more. It doesn't make any sense. You want to have something is safe and cost you less. Okay? So, the simplification, we don't have a refueling system. All we have is you have a crane, comes in, take the car out, put a new one. There's no refueling machine inside. Okay? We don't have a soluble neutron absorber. We have vulnerable poisons inside, and they reduce the reactivity delta K from 20% to 5%. So all I have to control with the control rods is 5%. No boron. And no boron means all the chemical stuff, all the cleanup, all that headaches is gone. Okay? Here's the important thing, the modularization. And here is the key. That's why I want IRIS with the I, international. To be economical, you cannot sell a plant, you sell one, and then you wait for the next order, you run to the church, lit up a candle, and pray for the next order to come. Okay, it doesn't work that way. What you want to do is to sell the reactor, the modules, around the world. So you have a base, you fabricate, and you're going to sell that, let's say, 15, 20, 10, 15 every year for these small modules. If you do that, you have to do on a global basis, on the world type basis. So what we call is a mass customization. So we have these various modules that are essentially the same. We may change a little bit depending on the country, but essentially it's a cookie cutter type. It's not one of a kind. It's a cookie cutter. You want to cut the cost that way and short the construction time. And the other thing that I already went through, the O&M is reduced because less refueling shutdowns, less initial shutdowns, and I can cut down the number of people. Because with the reactor basically runs on itself every 4 years. For 4 years. Really what I may exaggerate it, but really my goal will be to have a crew of babysitters. Okay? And of course it doesn't happen that way, obviously. But that's the goal, to minimize the crew, run the reactor, and that you minimize the O&M. The cost of the people cost is the number one. In terms of cost, BNFL has done a preliminary evaluation as a part of the review of the project, and they looked at low base, high data points, they looked at market clearing price of electricity, they have a proprietary economic model that they put all the numbers in, and then they came out, these are the results, then we sat down for about a week, several people, we reviewed it, does it make sense, and so forth. It's a top down, because we don't have the design yet to go bottom up. That's the next thing we're going to do next year. And the Vector, in fact, is going to work with us on doing that, verify. So for now, what we have, or what the BNFL came, these are the costs. And that is in terms of the internal rate of return, and it's 150, which is the top line, and the 300 megawatt, the bottom line. And basically, obviously, the 300 megawatt is less expensive, better cost. But at this point, I don't put too much stock on this evaluation. Let's realize all we've done, we worked for 9 months. We work like heck, we work night and day, but it's still 9 months. Okay? What I wanted is, if they came up with 10 and 15 cents a kilowatt, I say, well, I better find another line of job. Okay? If they come with the 3, 4, 5, well, in the ballpark. That's all it tells me. I'm not going to say I'm going to have 3 cents a kilowatt. I can't. But I say, on the ballpark, now we feel comfortable that we can do a bottoms-up evaluation. We actually design, start costing the equipment and see what it is. But we are there. We believe that economically it makes sense. In terms of economics, I show you one of the graphs that got the DOE people extremely happy. In the proposal, this is money we had. 480K for the three of us in the first year. Polyme is the Polytechnic of Milan, was kicking in 140K. So we leveraged the DOE funds by 30%. All the other people contributed, they came in with their own money, and we evaluated that that was about 10 full-time people working, covered about 2 million. So the leverage effort went from 30% to 400%. So that was my comment. This was in July when NASDAQ was flying high. And I told the DOE, look, invest with Iris is much better if you invest your money in NASDAQ. Okay, so they love that. The DOE really love that economics. The waste, we haven't done much work on this, obviously. But the principle is we have less spent fuel, we have less structures, we radiate. We are taking the consortium, comes in, delivers the fuel, delivers the best of everything, takes back. Okay? So if you're talking of a host country, a third world country, they are not stuck with the decommission. The Irish consortium takes everything back. What that means is we need an international repository. Okay? Not a Yucca Mountain, international repository. And right now, what I'm targeting is Russia. They need the money, and we're already talking with them. Okay? So that's basically the idea. It's international. And they will be partnering of Iris. That's, of course, there's going to be a lot of things that are going on. And God knows when we're going to converge. But that's the idea. Okay? So you have a place, and that's important. One thing that's important for utility is that you always have, say, okay, now I have a decommission. You're going to put extra cost of what is going to be and so forth. It's not decommission. That part is already included in the Iris price. The consortium takes it back. So the consortium fabricates, designs, and deploys. What it is, you have equal partners. Everybody contributes, everybody has a share, and we have the whole world is a market. It's not just a few countries. Okay? This is what I think which is important, the licensing. Our approach to the licensing is to have essentially two levels. As much as possible common. And we're going to have IEA to endorse, give the stamp of approval. I've been already talking with IEA quite a bit on that. Essentially, it's the same for all countries. That provides the basis. Then each country has a delta. And I said something is, for example, Japan has a different rules and so forth. Then you have a delta in licensing for Japan. But what this does, every time you have an Iris in a country, you don't go through the whole licensing process. You have something that is already done from the beginning and it stays there with the IEA. Okay? And the Iris will be for developed countries, for developing countries. It doesn't require a lot of infrastructure, so you can put whatever. Okay? But you can have independent variations depending on the country. For example, Japan doesn't care about 8 years recurring. They say, okay, we are happy with the way we're doing. They don't have any proliferation resistant concern because Japan is a developed country and they have it. So they say we stick with what we have. So in the case of Japan, you are going to have a core that can be refueled. So you may have some different versions. What I want to point out here is Iris is not going to be a static like it's been in the old days in nuclear power. What you had in a certain year, you still had 20 years ago. This is going to keep evolving. You are going to put more technology, better cost, better performance, and so forth. What that means is that the technological infrastructure of labs, universities, and so forth is always on the top. If you have an Iris type nuclear power, you always have, these additional improvements, additional technology. And Iris will provide what I call the flagship, is a reference point for the base tech program. And we have already started, and this is my last slide, we have already started that. As I said, we won 3 awards the first year with those 3 generation 4 reactors. In the second year, we won 2 additional awards. And this one is, of course, here why I'm here, and Lee invited me to tell you about Harris. And that was part of this NERI award that was awarded at the University of Tennessee. The other one has been with Ohio State, because one of the things that was concerned, you have a fuel there for 8 years. And they say, you're not pulling out for 8 years. And sure, I'd like to know what's going on. Okay, if I'm operating that reactor, I'd like to know what's going on. So I'd like to have an advanced instrumentation that can tell me what is the power deposition and so on. And that's what Ohio State is working. Something that lasted for 8 years is a fuel that tells me what is the power deposition and tells me time by time what's going on. So there are more things that are needed, and that is something that I want to talk to universities and labs. And the approach of Westinghouse is basically out of here you get almost no money, because I don't care about the money. What I want is to have the work done. And work universities, for example, say the work with Ohio State. Most of the funding is for your state, and the same thing is true here. Actually, the first year of this program, I work for free. Right? So that's so really that's the thing. We're not going into 50 or 100K. Doesn't matter. What is important is we are providing. Harris provides the focal point for this technological development for the various university labs and so forth. And that's all I have. I don't know how we're done with time, but a little bit.
We have time for a question or two.
Yes.
When we talk about high-pitch thermal reactors, what pops up in your mind years ago was the light water breeder reactor program based on the thorium-233 stock.
Right.
Did you do any looks at that before you went to process?
The thing that we looked at. The difference is, and that's what is the killer, is that was refueled. Okay, when you go 8 years, that's the problem. Is if you go for 18 months, 2 years, we make it. The moment you go 8 years, it's a different story. Okay, and that's what it was. And that was the thing that when we had the proposal, we looked at it and said we should make it. And because the breeder, the light water breeder didn't have obviously a positive work coefficient. What it didn't factor in was the fact when you had a lot of build-up fissile. And that's what we did. We should have thought, but we didn't. But again, we already found a solution, because if you put a fertile, at that point you go back, and it's a question of playing around how you do it.
What would you do to get the MOX out of the fuel? You're going to build your reprocessing plants?
No, the thing here is that the plant is very simple. And again, I have to sell the MOX. We're running covers. Iris now can take a MOX or can take a UOX. Independent. It's exactly the same vessel, the same power rating. It's just one core versus the other. The advantage of MOX is not, I was joking about BNFL. Obviously BNFL does, but even the French can do whatever. What it does, we take the MOX, it's there, okay? We burn it, and we put in Siberia. That's it. End of the story. All right. Yeah.
What are your assumptions on pinhole leaks or other fuel failure over the 8-year farm?
We have, of course, you go to say maybe we take 1% leakage or so. We have to look at. The idea is to go with, of course, it doesn't happen. And one of the key things was the choice of the cladding. And we looked at the various claddings, and we went with the zircaloy, because up to 70,000 burn-up zircaloys will make it. If we have to increase the burn-up, we're going to stainless steel. This is RS1. RSN is my personal opinion, is going to be CERMET. Okay. In fact, I already been talking with Brookhaven. We're going to have development of CERMET fuel, and that's one of the various aspects that we're going. And maybe 70,000 burn-up, I feel comfortable, because that's basically what we have now. So and we're going to have online monitoring, all the stuff. So if you now start pushing, I feel uncomfortable. That's with zircaloy. With the stainless steel, Well, the breeder went on 200,000, but it was in sodium. I don't feel as comfortable with water at 200,000. So really, my ultimate goal will be 70. I think the same will do it. But again, it's a technology. It may be Irish same.
Let me suggest that we end the formal question period now. We do have refreshments down on the second floor. Dr. Carelli will be down there, and he can answer more questions. And everyone's invited to the refreshments in room 219. Before we adjourn, let's express our appreciation to Mario.